I was feeling really pleased, at least when I looked yesterday. So good job, you guys, getting that done. And if you have not submitted your work to D2L, or if you had trouble with that, you can always email it. But email or D2L, if you haven't submitted your work, please get on that. Because remember, if I don't have your work, then you don't get a grade, because I need to make sure that you did your own work in our very virtual times. Oh, it's really echoey in here. Guys, we did this thing. Let me see if I can show you. So I'm in our playroom, but we're trying to transition it to be a home gym, you know, like kind of like sneakily move the toys over more and more into this little corner and, you know, get all our gym stuff there. So what we did was we ripped out the carpet and we got these big rolls of rubber flooring and then we floored. So let me see if I can show you. It's really cool. Okay. Can you see it? Isn't that awesome, guys? So it's like, oh, look, it's the gym. And it's all over the floor. Really exciting, but now that I'm in here doing a class, it's very echoey. That won't be too much of a problem. Great, I had to show you my floor, and now I'm all misaligned. I'll figure it out. Okay. All right, so I am recording. We've got 20 of us here.
I got a question.
I am recording.
I got a question about the showing work.
Sure.
Do we show like graphs work too, or how does that work?
So like the ones on where you're just looking at a graph to find the limit, you probably don't have a lot of work there. So if you don't have a work for that problem, then that's okay.
All right, thank you.
Yeah, basically what I'm looking for, guys, is if you have a problem with no work that I would have put work on, you know, or like normal people would have put work on, I'm going to be like, okay, I feel like there was some steps there that they probably should have written down, but you know, some things are so like even when some easy power rule problems probably don't need a lot of work involved. But yeah, so make sure you get that work in if you haven't already. We are just hanging a little bit low. There's our favorite glare. I don't know. Okay. All right, so here's what we're gonna do today. We sadly are still in chapter 11, but just for one section. Usually we tack this last section on to the next, you know, unit, like it'll be on the next test. But we do have one more section of chapter 11. So what we're gonna do today is we're gonna learn how to take the derivatives of two more functions. So we know how to do a lot of functions at this point. So you know, power rule got us those basic, you know, polynomial functions, and the chain rule helps, you know, when you have something in parentheses and you have power rule around it. And then product, we have the product of two things, or definitely we can handle a quotient situation. We can handle all of those at the same time. Honestly, guys, there's problems in the homework and on, you know, your exam where you use power, chain, and product all at the same time. So we should be getting really good and really comfortable at the rules like that. But we do have a couple more functions we want to talk about. Now, this list of ours on list of functions we can actually take the derivative for is obviously not inclusive. There's tons of functions out there, right? We don't touch the trig functions in this class, for example, so we're not going to be looking at sine and cosine and tangent and all that stuff. But we do need to look at a couple that show up a lot in the business or the financial realm of mathematics, because that's what we're here for, right? Let's see how this one works. All right, so this is 11.8. No. Guys, my kids have been playing with my markers and leaving the lids off. Frustrating. Okay, and just, all right, guys, I'll find one that works. Somebody's gonna be in trouble. What in the world, guys? Okay, this one works. All right, guys, so this is 11.8. Before, we haven't done a meeting in a while where I'm on the board. Is that the right direction? Or is it backwards?
It's right.
It's right, okay, thank you.
Yeah.
All right, so this is 11.8. We're gonna look at the derivatives of exponential and logarithmic functions. So exponential and logarithmic. You guys, honestly, you don't have to remember a lot about how to work with these functions algebraically, but we do have to know how to take their derivatives. So we're gonna start with the exponential. And guys, just as a recall, an exponential function is a function where x, your variable, is the exponent. That's why it's called exponential. So for example, we might have y equals 2 to the x power. So notice x is up in the power. That's what makes it an exponential function. You guys, when x is up in the power rule breaks down, you know, totally, guys. This isn't x to a power. This is something to the x power. So you can see right away that, you know, power rule is not going to work here. But you guys, we're actually not even going to take the derivative of all exponential functions. So I could put anything here. I could have 2 to the x, 3 to the x. I could have negative 55 to the x. They would all be exponential functions, but we're only actually going to learn how to take the derivative of one of those. You guys, it's the most important exponential function. And honestly, a lot of times we call it the exponential function because it's the one that has the most application. We are going to be looking at the derivative of y equals e to the x. This is the one. So you're not going to have to worry about something like this where we have an actual just whole number here. E, though, let's talk about e before I get started any further. E is not a variable, right? E is a value like pi, right? It's irrational. That's why we use a letter for it. Same with, you know, just like pi, guys. It's a decimal. It goes on forever. And e, not that you necessarily need to know to take the derivative of it, but it's this number here. It's like 2.71828, and it goes on from there. Not repeating, never ending, because it's irrational. But you guys recall for e. So e is a number. It's not a variable, so I can't treat it like a variable. So you guys, the derivative of e to the x, you're going to find is the easiest derivative rule we have. Hands down, simplest rule. But the proof to get there is probably the toughest proof if I were to prove it in the class. So it's kind of weird because we would have to go through this really tough explanation on why it's true. But the thing that is true, the derivative of e to the x, is so, it's awesome, guys. It's amazing. It's like the easiest one to remember. And I'm going to show you what it is. So you guys, let's say we have y equals e to the x. The derivative, so y prime, you guys, the derivative of e to the x is itself. It's e to the x. And showing how this is accomplished, you can look at your book if you want, but even in your book, guys, they skip a lot, and they say they do. They're like, hey, these few lines aren't really in the scope of this class, so we're just going to skip over them. But, you know, if you're very, very curious, we can talk about it. But what they do is they take e to the x as the function, and you put it in the definition of the derivative. So the f of x plus h minus f of x. This is what happens after a lot of mathematical magic, basically. But yeah, it happens, guys. You start with y equals e to the x, you take the derivative, and you get the exact same thing. You guys, the e to the x is its own derivative. So that's the first rule we want to talk about. You guys, this is pretty amazing, right? And it's not too hard to remember. And then we're going to use it in some examples. So obviously, I can't go with, this is the simplest example. Start with e to the x, take the derivative, still e to the x. I can make it a little more complicated. Maybe putting it into a function with other things. So if I have, let's do function notation this time. You guys, let's do f of x equals 2x cubed plus e to the x minus 7x. So now we have an exponential piece of a function that otherwise looks normal, like we've been dealing with. You guys remember with derivatives, you take one item at a time, so they don't all have to be the same. One rule doesn't have to cover the entire function, right? So we're going to take one at a time. So we know how to use the power rule at this point. And you guys, at this point with the power rule, I'm going to stop doing as many steps. I'm just going to be writing, you know, because you're probably at that point too. So you guys, the derivative of 2x cubed is 6x squared plus the derivative of e to the x is itself. You guys just keep it the same. That's the derivative. It's e to the x. And then minus 7x, I know that becomes minus 7. So it's, you know, power rule is applying where it applies, and our exponential function rule is applying where it applies. Let's look at this one. Let's go back to just the exponential term. Because it's not always just e to the x that we have. There's a lot of versions of the exponential function. X is always going to be in the exponent, and there is always going to be an e here, but x doesn't have to be alone up here, and sometimes it's not. So you guys, chain rule. You guys, we have chain rule for an exponential function, and it's a lot harder to see what is happening as far as what's the inside function and what's the outside function, okay? So just stick with me. We're going to work this problem together. Believe me that it is a chain rule situation. So you guys, why is it chain rule? It might be your question. Well, because the exponential part of this function, the e part, is the outside function. Anytime that you have an e in your function and you have to use chain rule, e is your outside function. So what I'm saying to myself is, I need to take the derivative of this function as a whole. Remember where, just like I did before, where I had parentheses and stuff like that, I said, just pretending it's just e to the x. Remember, it was always, pretend this is just an x. Now, what do? Pretend this is just e to the x. How do you take the derivative of that? Well, I just showed you. It comes down exactly the same. So the outside part of the function is really easy on the derivative. I take whatever is here. Because it's exponential, I write exactly that same thing here. You guys, this is my first step in doing the chain rule on this problem. And remember, when we had the chain rule before, that term in the parentheses, sorry, we brought it down exactly the same, right? So this 3x, you guys think about 3x being your inside function. And even though at some point I have to take the derivative of that too, remember, in the big picture function, in the exponential, it has to come down exactly the same. So for chain rule on an exponential function, your first step is going to be to bring your e term down exactly as is. Your second step is to complete the chain rule, guys. The second step is always taking the derivative of what's up here and sticking it on with multiplication. So, you guys, what's the derivative of 3x? Well, that's just 3. So you just get it times 3. And you guys, we end up with 3. You can put that in the front. It looks a lot better. You guys, that's just 3e to the 3x. So let's do another one of those. Chain rule with an exponential function, if we had learned it first, like if this is how we learned the chain rule, it would be so much easier, but because usually we're dealing with polynomial functions, we start there. So you get used to that and you start getting a little complacent and thinking, oh, this is the only type of function where the chain rule is going to apply. But you guys, the chain rule applies anywhere it's necessary in any function. You just have to be able to recognize it. So let's do another one. Let's do f of x equals e to the negative 5x. So one thing that's beautiful about these exponential functions is it really doesn't matter what's up here. This negative 5x, I don't have to think about that going to the bottom of a fraction or anything like that, you guys. I'm just going to do it as is. Just like we deal with negative 5s or negative powers in the power rule. We still just do it, right? We just bring the negative along. It's kind of like that here. So I'm thinking if this was just e to the x, no chain rule necessary, I would bring it down. My answer would be e to the x, right? Because it is its own derivative. And you guys remember the e part is your outside function. Your first step will always be to bring this e term down exactly as is. So that is my first step, and it doesn't seem like I'm doing anything there, but remember, bringing it down exactly as is taking the derivative of the exponential function. So I took care of that part. Don't forget to take care of this part. You guys, now, what's the derivative of negative 5x? Well, it's negative 5. Just stick it on. Gotta get a negative in there. So you guys have to put that in front and call this negative 5e to the negative 5x. So I want you to see a pattern in these two. When you have e to a coefficient times x, so just 3x, or in this case, negative 5x, what ends up happening is that this number ends up, you can put it down in the front. Notice that's what happened here. It's a 3 here. We ended up putting a 3 in front. But you guys, I don't want this to confuse you because it kind of looks a lot like power rule, right? You're like, oh, the 3 and I put it in front and then I take one away, but we don't take one away. This is chain rule, remember? This is how we got there. We got there through the chain rule. So at no point whatsoever do you want to ever try to implement power rule on an exponential function. And I'm saying that now, you might say, well, that doesn't cross my mind, but it will. You guys, it will, because we do this a lot. And what happens is we take this number here, the negative 5, for example, and we bring it down in front, forgetting that that's because of chain rule. And it's really tempting to want to take one away. You say, oh, I bring it in front and then I take one away. We do not take one away. Guys, your exponential function stays exactly the same. Okay, so let's do some more of the chain rule plus the exponential. We'll do one more really straightforward one, just like this. So let's do a y equals e to the 10x. So again, really simple here. What's happening? Well, the first thing you're going to do is say, well, okay, I'm going to bring my exponential statement down just as is. And then where's the chain rule kick in? Oh, yeah, I have to take the derivative of my exponent, which is 10x, and multiply it right here. So the derivative of that is 10. And again, sorry guys, this is derivative, I didn't mark that. And I end up with 10e to the 10x. You guys, you don't always need this extra step. You will figure out that what happens here is this number, you put it in front, and as long as you don't change it when you write it again, that's all there is going on here. You can see where it came from. I like to show, you know, this is where this is coming from with the chain rule, but at a point, you're gonna shortcut that. You're gonna take that number, you're just gonna stick it in the front. And again, as long as you don't change it up here, it's gonna be perfect. Okay, so let's make it a little bit worse or better or more fun, depending on, you know, your level of interest, right? So what if I've got y equals e to the 3x squared? So there's more involved here. You guys, if you have an exponent, your exponent, that seems like a lot, right? You guys, it happens. There can be anything up there. As long as there's actually an x involved, it's fine. And we're just gonna do the chain rule again. Honestly, I think that chain rule on e functions is a little bit easier, in my opinion. It might not be to you, and if it's not, that's okay. I just like it better. I think it's really clear to see what's what. But here we go. Remember, the outside function is always the e term, and it always comes down exactly as is. So this e to the 3x squared is going to come down exactly as is, as e to the 3x squared. But we're not done, because now I have to take the derivative of the power, so of the 3x squared, and stick it on with multiplication. So what is the derivative of 3x squared? Well, that's 6x. So I'm just going to tack it on. You guys, it's just another link in the chain. And you guys, this is the right answer. Usually when you have like x terms and e terms, we usually put the x in the front. So the way I would write this would be 6x e to the e to the 3x squared. But this would probably be fine too. If you wanted to put it in like that, it'd probably just be fine. So chain rule with exponentials, bring the term down exactly the same, and then take the derivative of the exponent. That's all there is to it. Let's do one more, and then we'll move on to the logarithmic function. Okay, so example, I got f of x equals e to the 4x cubed plus 5x. So making it a little bigger every time, right? It has more than one term. That's absolutely fine. You guys, both of these terms right now are in the exponent. You guys, they are part of this e term. So my first step, remember, is to take the e term and bring it down exactly as is. So we do all of that with all of those terms. So I get the derivative is going to be e to the 4x cubed plus 5x. But now what am I going to do? I'm going to take the derivative of what's up here and stick it on with multiplication. So let's do that. Times, in parentheses, guys, notice your derivative is going to have two terms. Make sure you parentheses that because they both need to be multiplied by the e, right? So we're going to get 12x squared plus 5, like this. And you can write that however you want to write it. You can leave it just like this. You could put the 12x squared plus 5 in the front. Just know that you're not going to take that e term and actually multiply it out times anything. You're going to leave it in some like this somehow. Guys, whether you put that in front or behind, doesn't matter. So guys, there's not a lot of times where e to the x is just e to the x because it's too easy, right? I mean, I can't ask you a bunch of homework questions that are all derivative of e to the x and you're just going to keep writing e to the x the whole time, right? So there's a lot of chain rule involved. There's a lot of us putting stuff up here. So I think the chain rule with the exponential is the most important thing to get out of this stuff. just remembering I'm going to bring the whole thing down exactly the same as it started. And then I'm going to take the derivative of the exponent and put it next to it with multiplication. So let's talk logarithmic function. You guys, it might have been a while since you've looked at logs. Again, it doesn't really matter how much you remember about logarithmic functions. What matters is that you can take the derivative of them. So let's talk about the only logarithmic function we're going to talk about. You guys, there's a lot of different log statements, right? Every time you have a logarithmic function, it has a base, if you don't remember. So log base 10 is very popular. You guys, you can find that button on your calculator. If it says LOG, that's log base 10. But you can take any base, you guys. You could have log base 5 or log base 100 if you wanted to. And all of those different bases, we change them to meet our needs at the time for the application we're looking at. You guys, there's only one base that we're going to talk about, and it's base E. So we're back to the E's, guys. Where's my, oh, there it is. We're back to the E's, guys. E's are so important, you guys. If you didn't have this E term, you wouldn't have a formula for compound interest that compounds continuously, which is very important. There's so much we wouldn't have without E. So it's why we focus on it in this class, because of the financial implications. The business implications are very strong. So anyway, we're going to talk about log base E. So log base E, you might write it like this, but it's not how we write it, right? If you remember anything about logs, well, this is a fine way to write log base E. Because it's base E, and E sometimes is called the natural number, we use the term natural log when we want to describe log base E, and we don't use LOG, right? We use LN. So log natural, if you want to remember it that way. And we don't write a base here. You guys, because it says LN, we know it's log base E. So anyway, just a quick recall. When I start writing LN, and I want to make sure you know what that is. So let's look at our function. So you guys, another thing I might mention is when you have a log function, so this is where your input goes. It's not just an ln by itself. The L and the N aren't just two variables multiplied together, right? This is notation. You have the natural log statement, but there has to be something here that you put into the natural log function. So, sorry. So we're going to do y equals the natural log of x. So here's your input. You're putting x into the natural log function, and natural log x is how you're going to see this function written, like in your book or in your homework. Or it could say f of x equals natural log x. But what happens when you take the derivative? And again, this one is a little bit past our scope as far as like a proof of this goes. But I'm sure you trust me. So if y equals the natural log of x, and we take the derivative, what we're going to get out is that the derivative of this is 1 over x. So not as nice as e to the x, where it just saves itself, right? I mean, that you can't get better than that. But this is pretty straightforward too. You have natural log x, 1 over x is the derivative. Now, where natural log gets hard is when you start sticking the chain rule in with it. So we'll go over that, of course. But you guys, anytime you just have natural log x, and it's like this, and it's just an x here, it's always going to become 1 over x. Okay. So I want to, before we move on, I want to be really clear. Whatever is in here, whatever your input is, This time it's just x, and that's what we like, right? But remember, it can be more than this. And if it is, what happens is, instead of saying x here as we recite this, I want you to think, anytime we have the natural log of something, it becomes 1 over something, because it's not always just an x. Whatever you're sticking into that natural log statement, to take the derivative, it has to go on the bottom. So let's keep that in mind. So I want to do y equals the natural log of 3x plus 2. So I think to myself, okay, how does natural log work? I take the natural log of something, and when I want the derivative, I have to do 1 over that thing. Okay, I can do that. So I take the derivative, it becomes 1 over 3x plus 2. But do you think I'm done? I don't think I'm done, guys, because this looks a lot like a chain rule situation to me. The outside function being the natural log. I took care of that by doing 1 over that thing. But this is not just an x. If you can ever say that in any function, right? But this is not just an x, you know you got chain rule in there. Because this is not just an x, I have to take the derivative of what it is and multiply it on the end. One thing that's nice, the rule of chain rule, while its form changes, you do it on different functions, the actual rule never changes. You take the function derivative, then you take that extra derivative, and you always stick it on the end with multiplication. It always works the same. So, guys, I need to take the derivative of 3x plus 2, which is not just 3, and I just need to multiply it here. Now, I want you to be really careful, because this is a 3. This isn't a 1 over 3. I can't put it on the bottom. You guys, you're going to put this value on the top, because it's a whole number 3. It's not on the bottom. So the way I would write this, guys, would be 3 over 3x plus 2. This is the derivative. So notice your natural log statement does go away. When I put this 3x2 on the bottom, that takes care of the derivative, and the derivative does not involve that statement. Don't try to stick the natural log statement in here anywhere. You guys, once you do take the derivative, it's gone. Let's do another one. So you guys, I want to do the function f of x equals the natural log of 5x squared plus 3x. So you guys, my first step is to take care of the big picture, the natural log situation. This is the natural log of this, all of this. So when I want to take the derivative, I'm going to put 1 over all of this. That is the act of taking the derivative of the natural log statement. So I have 1 over 5x squared plus 3x. And it would be great if I could be done there, but I'm never done there, guys, because this isn't just x. Because it's not just x, first of all, let me rewrite this. Because it's not just x, I'm going to tack something on to this. I was worried about space. But you guys, what am I going to tack on? The derivative of what this is, right? And this one's going to have multiple terms. So you guys, the derivative of this is 10x plus 3. And I know anytime that I tack on a derivative with more than one term, that I do need parentheses. And you guys, all of this, these are whole numbers, right? I'm multiplying by this term. So I'm never going to stick it down here. You can always, always take the derivative you get at the end and stick it on top. So the way I would write this is 10x plus 3 over 5x squared plus 3x. So I know that this is a lot to take in. You guys, exponential and natural log might not even have crossed your mind in a long time, let alone taking the derivatives of them, which is that, a very new concept to us. So these are definitely going to need practice, and later this afternoon when I get your homework up, you'll see a lot of practice, and that will help you a lot figuring this stuff out. Let me see. There's a couple I want to do because, we combine so many things, so many rules into one problem sometimes. Sometimes 3 or 4 rules show up in a problem. These problems today, even though they were exponential and natural log, obviously we saw the chain rule a lot, but we've used power rule multiple times without even thinking about it, So it all works together, and you have to be good at all of the rules because you never know when they're going to show up in a function. I want to do one more. So guys, I want to do f of x equals e to the 6x squared times the natural log of 5x. So you guys, I want to put our 2 new functions together into a product situation. You guys first of all, can you recognize this is a product rule situation? I have an x term here, or a term with an x in it here. I have a term with an x in it here, and I cannot effectively multiply these together, right? There's nothing, you just write them next to each other. That's all you can do. There's no way to actually combine these terms into one. So you have to be able to see the product happening here. You guys, I'm going to say that the e term is my u, and my natural log term is my v. And we know where to go from here, guys. We know the product rule like the back of our hand, right? So u equals e to the 6x squared. Let's find the derivative of u. That's in taking the derivatives for u and v is where we're going to use the new stuff. So what do? Let's remember. I bring this e term down exactly as is. So it's going to come down, and it's still going to be e to the 6x squared, but I'm also going to take the derivative of the exponent and multiply it here. So that's going to be 12x. So your u prime is going to be 12x e to the 6x squared. Just put it all together. This is the derivative of u. Let's go over here and talk about v. So this is what we started with. V is the natural log of 5x. This one should be really fresh in our mind, guys. If I take the natural log of something, the derivative is always 1 over that thing. But I also have to consider, because this is not just an x, I multiply by the derivative of 5x. And that's just 5. And remember, that can go on top. You guys, listen. Look at an interesting thing that happens here. You guys, when I put this 5 on top and I get 5 over 5x, would I leave it like that? I wouldn't write it like that, right? Because there's a 5 on top and bottom. Notice what happens. I just end up back at 1 over x. You guys, this is a thing that happens on certain natural log problems, and I don't want it to throw you. It's just, there's a coefficient here and it seemingly just went away. That's okay. I don't want you to take a shortcut here. I don't want you to see this and say, oh, it's just going to become 1 over x. I want you to use the rule every time, even if this happens a lot for you. Write it just like this, use the chain rule, see those values cancel out. And notice we just ended up with 1 over x, which, yes, it's interesting because we thought that 5 would show up somewhere, but it ends up that it doesn't, just in the process, and that's okay. But you guys, now we have derivatives of u and v, and we already have u and v, so let's write out your product rule. So the derivative of this function f of x, remember it's u times the derivative of v plus v times the derivative of u. So here's u, e to the 6x squared, times the derivative of v. Remember, we just found that was actually just 1 over x. Plus v, which is natural log 5x. I gotta erase stuff. So here's v, natural log 5x, times the derivative of u, which is all of this nonsense over here. So times 12x e to the 6x squared. Now, we did the product rule. You can, sorry, what was this? F prime x. There's a lot of different ways you can go from here. Simplifying wise, there's sometimes, and I almost bet that MATLAB's probably going to take, notice both terms have e to the 6x squared in them. I bet you anything, they're going to factor that out and put it out in the front. Would I do it? Not necessarily. You guys, I would, just like we found out on your last homework, that very first line where you actually implement the product rule, you can put your answer in like this, no further simplification, and it should take it. So you guys, that's all we did. You can see u and dv and v and du. Write it in just like that, and it should take it just fine. But you guys, what did we do here? How many rules did we just use for this one problem? Well, exponential, logarithmic, chain, of course, power rule, and product rule. You guys, all in the same problem. I understand that this is a lot, and that's why you're going to have a lot of practice on it. But with that said, that is, while it is a lot, at least we get to stop here, you guys. And another thing that's nice is at this point, we're done with chapter 11, so we get to move on to some applications, which is fun. So yeah, you guys, I'll be looking over, there's a couple problems in your exam, problems that require more work than others that I do look over for partial credit. There are some problems that really don't call for it, you know, like really simple, like looking at the graph and taking the limit type thing, you know, but there are some problems that have a lot of work that I can give some partial credit on. So as long as I have your work in D2L, then expect me to be looking over this list of problems that I have. And if you see your grade changing just a little bit, like, you know, you see a few points up, not down, it won't be down, just up. Just know it's because I'm just reviewing your work and any like good things you did, you know, I want to give you some credit for that. But also remember that it's not going to be on every problem. So I don't want you to, you know, get concerned about that. Just a couple of them you'll see. Other than that, if you haven't turned in your work yet, definitely get it in. Remember, that's like the biggest thing right now, because whatever MATLAB says you have on your test, if I don't have your work for it, it's going to disappear. So you definitely want to get on that. And I think that's all I have for you guys today. So I will just see you on Wednesday.